In the previous video, we looked at Kc, which is an equilibrium expression involving concentrations. But typically we observe reactions involving gases, so we need to look at equilibrium expressions involving gases, and we can compare and contrast the two. So gases are typically expressed in terms of pressures. So when gases are involved, the K can be expressed in terms of partial pressures. This is known as the Kp. So if we have a particular equilibrium expression that is 2NO gas plus Cl2 gas in equilibrium with 2NO Cl gas, we can write a Kc expression for this to be the concentration of the products, which is NoCl, that quantity squared, divided by the concentration of the reactants, which would be NO squared, times the concentration of Cl2. Our Kp expression we can write as, instead of the concentration of NoCl, the partial pressure of NoCl, that quantity squared, divided by the partial pressure of NO, also squared, times the partial pressure of Cl2. Okay, so the Kp values we need to know are expressed in terms of partial pressures. So what happens when we look at Kp versus Kc, and what is the relationship? So let's look into the relationship between Kc and Kp. So we remember PV equals nRT, and if we rearrange this expression to be the pressure equaling N divided by V times RT, and we look into the units, N is moles, volume can be expressed per liters, and this is like a concentration term. So our concentration term here will allow us to rewrite this equation to say pressure is equal to the concentration times RT. Okay? We can express Kp in terms of partial pressures, so this can be written as Kp. We can express Kc in terms of concentration, so this will be Kc. Okay? Here, we then can multiply this by RT, and the relationship here happens to be between the delta N, or the difference in the number of moles, and this delta N right here is going to be the difference in stoichiometry of gaseous reactants and products. And we'll express this as products minus reactants. So let's come back up here and look at this reaction where we have 2NO gas plus Cl2 gas in equilibrium with 2 NoCl. We can say that over here on the reactant side we have 3 moles of gas, and over here on the product side we only have 2 moles of gas. So our Kc and our Kp are going to be different. All right, so the Kp is going to equal the Kc times the quantity RT to the delta N. In this particular case, we need to take products minus reactants. So we're going to have our delta N that we can write for this is going to be our Kp is going to equal Kc times RT times 2 minus 3, or to the minus 1 power. So if for this particular reaction we're given the Kp, so if the Kp for this reaction is going to be 1.9 times 10 to the minus 3 at 25 degrees Celsius, we can determine the Kc. So the Kp is going to be 1.9 times 10 to the minus 3. That equals the Kc times R, and in this case, remember, we're using the ideal gas equation here, so we have to use the 0.08206 liter atmospheres per mole Kelvin, times the temperature, 25 degrees Celsius. We need to convert this to Kelvin, or 298 K. And all of this right here is going to be raised to the minus 1 power. And our kelvins here are going to cancel. If we go through and do the algebra for this particular expression, Kc is going to equal 1.9 times 10 to the minus 3 divided by 0.08206 times 298 to the minus 1 power, and Kc then equals 4.6 times 10 to the minus 2 molar to the minus 1. So this is an example of how we would convert back and forth between Kc and Kp.